about some fundamental concepts that are important to study groundwater transport or groundwater pollution. And one topic that we were talking this morning was concentration. What's concentration? Can someone give me a definition? Okay, so there are many ways to define concentration. One way would be to say a mass of some pollutant X per liter of solution. So if you have liquid as our solvent, like so the denominator is related to solvent. Is related to solute. Okay. So if I do write mass of X per liter of X, is that a concentration? Yes, no, maybe are the three answers. No? What is it? Right. So we usually call this density. In petroleum engineering literature, they don't make a distinction between density and concentrations. They call all of that concentration. So in some form, it is a concentration, but the idea of concentration is you're normalizing your mass with respect to something, like that something being liter of solvent in groundwater or in liquid systems. Can we write concentrations for solids? So if I have a bunch of soil and I have a contaminant on that soil, right? So I have soil, the soil is contaminated. So I can extract whatever the contaminant is. So typically what we do is we take that soil, wash it with whatever we want to extract, and then pull out the chemicals, and then we measure it using conventional techniques like GC, LC, HPLC, whatever technique you use, and that will give us the mass of X, right? So I can get this mass of X from my soil, so I can take a known quantity of soil and I can extract and calculate that mass of X. What about the denominator? This is solid, so can we define volumes? Can I have a liter of soil? No? If I take soil and put it in a measuring jar, fill it up to 1 liter, okay, then I pour that into a solvent and extract whatever I want to extract out of it, am I not getting mass X per liter soil? What could be some problems with that type of measurement? So what I'm doing is I have a beaker, right? Right. So this is 1 liter. I fill it up with soil, right? And then of course there is some pollutant on that soil. I want to extract this. This gives me the mass of X. The problem is this liter of soil is very poorly defined. Okay, what could influence that liter of soil, or what influences that liter of soil? What density? So more fundamentally, can I have, for a known mass of soil, can I pack it or put it in different ways? Technically I could, it depends on how you pack that material, okay? So that's why we don't use lateral soil. So what happens is in the morning, people talk to, Dr. Cecilia talked about subsidence, right? So what happens during subsidence? Compression. So so we have water, we pump groundwater out, and it causes subsidence, okay? The reason that's causing subsidence is because some of that force, okay, or the stress, okay, that's being provided on the aquifer by the atmosphere as well as all the above overburden that's on the ground, part of that is being taken up by the sand grains, part of it is being taken up by water. So if I remove that water, that excess stress will now has to be taken up all by that sand grains or or the aquifer material, okay? If that aquifer has clays, what happens? What are clays? Right. Do you know what a clay is? What will not provide any resistance? The clay has water, okay? So we can actually dewater the clay. The clay pores are very, very small, okay? So the problem is not that it's harder to pull water out of the clay, but if I put enough pressure, I can pull that water out of the clay. So that's usually not the problem. The problem is if I can put back water, then there won't be any subsidence, okay? The reason there is subsidence is because clays, can anyone tell me what a clay is? What's a clay? How can I define a particle and say that particle is clay? Okay, so the way civil engineers have defined clay is using size of the particles, okay? We say if it has a certain size, if it passes through a certain sieve, that's a clay, okay? Moisture content? So, but the way clays are defined by soil scientists is clays are actually layered silicates, okay? And in the middle, either you have a sodium or potassium or calcium, some sort of a cation is here, and the hydroxyl surface is here. The negative charges are here, okay? So clays are particles that have a net negative charge, okay? So this positive charge kind of keeps moving back and forth to keep this plate open, okay? So this positive charge is usually associated with water that's in here. So there is water sitting here, okay? So when I pull water, I pull out that positive charge, okay? So I'm left with two plates that are negatively charged. What happens to those two plates? They have to repel, right? Because so the plates don't sit like this, they'll sit like this, because this is the least amount of, gravity is still pulling this plate down, and so what happens is this will be the least configuration where they'll have least amount of repelling, so they'll be most repelled at this state, and accounting for gravity. So when we try to push water into it, we are not able to push that water, okay? So if the clay plates were to fall like this, we were able to push that water and there wouldn't be any subsidence next time it rained. But what we're doing fundamentally is changing the structure of that particle, and because we're changing the structure, we're pulling out this middle portion. We have net negative charges that repel and fall, and then the water never goes back, and we have subsidence. Okay? For our discussion of concentration, what happens is the amount of water that's in there will define the volume, okay? And that can vary in soils, okay? In aquifers, you're fully saturated with water, but in soils like the vadose zone or what we call the upper portions, you have air, water in your system, so your density changes based on how much water is there, because the air doesn't add to the mass. But nonetheless, that air and water keep the particles in a certain arrangement. If I remove that water, my arrangement is changed, and so will my volume change. My mass will not change significantly because I'm not removing the solids where most of the mass is, but I'm changing the volume. Okay? So typically for soils, we don't use the length of soil, but liter of soil, but we write it as mass of X divided by mass of solids or mass of dry solids is how we define concentration in soils. So when we study aquifers, unlike traditional wastewater treatment where milligrams per liter works for us, we have to look at concentrations that are written in multiple ways, like one either as mass per length, mass per volume, or mass per mass. Okay. So now, is mass the only thing we can use to define concentrations? Can we define it using something else? If you have bacteria, for example, if you're interested in modeling bacterial transport, we don't usually say milligrams of bacteria, but so we represent it with some numbers, right? Colony forming units or MPN, the most probable number, whatever per liter of solution, so it could be a number, okay? So it could be a count of some sort, okay? And what else can we use? If you're a chemist, they would frown if we use milligrams per liter. So milligrams per liter is a very engineering thing, parts per million is the same as milligrams per liter, okay? Molarity or molality, or moles, okay? So what's a mole? What's a mole? Can anyone define what a mole is?
What is the amount of substance
per unit weight?
Is the number of
weight upon molecular weight.
One molecular mass dissolved in 1 liter solution. 1 liter solvent.
Okay. That's molarity. Okay. What's 1 mole? Correct. It's 6.023 times 10 to the power of 23. Okay. So a mole is what? It's basically a dozen for a chemist. Okay. So because they're dealing with a very large number, it's still a count. Because you're counting the number of molecules, a number of atoms, or number of something that's there. If you have 1 mole, you have 6.023 times 10 to the power of 23 of that. So if you write it in moles per liter, actually we're writing it in terms of counts per liter type units. So concentrations can be expressed as either moles or counts or whatnot. So we need to have some basic understanding, but there's some more things, some more concepts that we need to learn or kind of refresh from our fluids or from our soils, from our undergraduate classes before we go study this. Okay. So why do we study groundwater? Dr. Cecilia gave a very good overview this morning as to why we study why we are interested in groundwater. Why are we interested in groundwater? Groundwater, why? So actually groundwater, there's more groundwater in this world than there is surface water. Okay. And a lot of fresh water that's there is groundwater, because the remaining portion of the fresh water is either in glaciers or someplace. So even in places where there is a lot of surface water, people still use groundwater because chances are it's fresher. Okay, so that's one reason why people study groundwater, right? Or we are interested in groundwater. Who is the biggest user of groundwater? Who do you think uses? Which sector uses the most amount of groundwater? Irrigation. Okay. Why? Surface water is not available at every site. So what is very appealing about groundwater is its availability. You can put a well and you can take it. Okay. What's also very appealing about groundwater from a legal perspective is in many parts of the world. Okay. This includes highly developed westernized world, there is no regulation on groundwater. Okay, California, she was talking about California this morning. Groundwater is not regulated in California. People can go put a well and get water. Okay, in many parts of Texas, that is the case, where people could go and put a well and get Texas. So there was a case in 1905, or like, this was a long time ago, 100 plus years ago. So there was railroads being put in the U.S., and they wanted to put a railroad in Texas, and the company said, well, to put railroad we need water because we need to use it for construction, right? So they wanted to put a well and pump water and produce that water for railroad construction. There was a farmer who was using that groundwater to produce his crops. He said, hey, wait a minute, you can't be putting a well and taking water, because if you do that, I will not have water for my crops. So what did he do? He said, okay, I'll go to the court and sue this railroad company. So he sued the railroad company, and in the lower courts he lost. The people came and said, well, they're a railroad company, they can do whatever they want. It's their water. Okay, you keep your water, they'll keep their water, and everybody's fine. But of course, water moves from one location to another location, right? So the court went on, it eventually went to Supreme Court, and in Supreme Court, they said groundwater is so mysterious. We don't know enough about groundwater, because it's underground. We don't know how to study it. We don't know what it is, and as a result, whoever owns the land owns the groundwater. Okay, so much so that the court went out to say that if your pumping causes harm to your neighbor, that's okay. Okay, you just can't go into their land and pump without their permission. That's the only thing you cannot do. Okay, of course you can put a well and suck your neighbor dry, and that's fine. But it has to be on your property. It can't be anywhere else. Okay, so because of that, we call this the rule of capture. Whoever captures the groundwater has that groundwater. Okay, and it's also called the law of the largest pump. The reason it's called the law of the largest pump is you put a bigger pump, you can suck more water towards you. So it's not that in 1905 people did not know this. They just didn't want to regulate it because they didn't know how to regulate this groundwater. So because of the poor regulation, the access to that groundwater is very easy. If I want to get surface water in Texas, I have to go get a permission from the state. I have to stand in line and say, hey, I need to use water for this purpose. Okay, the way the water is regulated, the way the water is adjudicated in Texas or in many parts of western United States is, if you are first to ask for water, you have the first preference for the water. It doesn't matter where you are on that stream. You could be away from the stream, but if you are the senior most right holder, you get the first priority. Okay? And because of that, what happened? If you are the last person to come in line when there is drought, it's like movie tickets for whoever, Shah Rukh Khan or whoever's movie on the first day, right? You stand in line, the first few people get the tickets, and then the last guy may or may not get the ticket. So that's what happens is the last persons don't get the water, and that's very much a possibility. On the other hand, groundwater is not regulated, so people will say, one thing where I can get it almost without any regulation. On the other hand, I may or may not get this water, so people start using groundwater. One of the other things that happens is groundwater gets used a lot more during periods of drought. So what I show here is the groundwater to surface water use in Texas. Okay, the wet periods are when we have a lot of rainfall. The normal periods are when we have typical rainfall in Texas, and then the dry periods are when there is drought. Okay, and the PDSI there is the Palmer Drought Severity Index, which is a measure of drought. How do you measure drought? And that's one way to do it. And what do you see? The median, which is the black line in between, is over 1 during periods of drought, okay, and much lower than 1 during wet and normal periods. So groundwater use almost doubles during periods of drought because there is no surface water dries up, and people who have junior rights don't have surface water, so their next choice is to get groundwater. Okay. Well, what you see is that some places it is below 1. The reason for that is there are places where we regulate groundwater, and we say if you're in drought, you shall not use groundwater. So there are parts of Texas where there is regulation of groundwater, but there are parts where it's not, and there are some places where it's over 2, like so they become heavily dependent on groundwater because their surface water supplies are not strong enough. Like they can only work during wet periods. They'll not work during dry periods. Okay. So this is one part of the problem. One part of the problem is there is a lot of groundwater being used, and our reliance goes up as we go into periods of drought. Okay, so that's one part of it, which is the quantity part of it. What about the quality part of it? We said groundwater is of slightly better quality than surface water, right? That's generally true. That's not always true. Okay, but there are certain things like total sediments, total suspended solids. You will not see that in groundwater. Okay, so very rarely will you see phosphorus because a lot of that phosphorus is associated with the sediments. So if you don't have the sediment, you don't have the phosphorus associated with it. But you will see a lot of different things, both man-made as well as natural contaminants that occur in groundwater. Okay. So we'll look at some of those in the class. But the big part that we are interested in this class is to look at a source of contamination. Typically, this source can be a point source or like a localized source, or it could be a diffuse source, which means the source exists over a very large period of time. Okay. We'll also look at what are some of the sources that come in. But typically, we have what's called as an underground storage tank or some tank that stores a chemical, and it breaks. Okay. When it breaks, all the chemicals in it will start moving. Okay. Typically, these tanks are never placed underneath the groundwater. Okay. We are smarter today. We don't do these things. Okay. There are times when we used to do this, so we don't. So it's above, and as the chemical moves, okay, most of the movement in the vadose zone or the upper portion. So there is water table, that is that dotted line there. Anything above the water table is called soil or the vadose zone. Anything below the water table is called an aquifer. Okay, though I'll give a much clearer definition of aquifer fairly quickly. So we have a source. It's got some chemicals. That could also be a septic tank, which means it could have some microbes. For the purposes of this class, all biological, physical, or chemical constituents are all chemicals for us. Like we basically deal them like chemicals. Like, so if it leaks, it moves fairly vertically downwards under the influence of gravity. Okay, because in the vadose zone, what characterizes the vadose zone is you have the solid phase, you have the water, and the air. Okay, so the pore spaces are filled with water and air, and the solid phase is your solid matrix. Okay. Can this be saturated? Can I only have one phase? Can it all be water? This is all underground. So this is our land. Okay, there is that house. So it kind of tells you this is our land. This is where the water table is. Okay, so if I keep drilling a well, at some point I'll see water. Okay, so that's the water table. Okay. If I go below that, I have solids and water. My pores are completely filled with water. Okay. Up on the top, above that water table, I have what's called the vadose zone or the unsaturated zone or the partially saturated zone. Now, what happens in that partially saturated zone is I have solid phase, which are your rocks or soil materials, but you also have water and air. Okay, so there are two fluids in this pore space. Okay, there is only one fluid in this pore space in the aquifer. Okay. When it rains, some of the upper portions might be fully saturated with water. So there are times, small periods of times where you might see complete saturation, but by and large, it's unsaturated, which means you have air and water in it. Okay, And can we get rid of water? Typically not. So what we have are what are called water wetting systems. Okay? So our rock matrix, if I take a rock, usually there is a small coating of water that's associated with it. Okay? Because water, what's water chemically? Okay. And what is this angle?
104.5.
Correct. And the reason we have that angle is because there is charges. Okay, so there's van der Waals forces, right? So what happens is, as I said, clays, they have some charge associated with it. So most of your mineral matrix will have some sort of a charge on the surface, and the water will attach to itself. So there is always a small coating of water on most minerals. The only exceptions would be if you have something that's very organic, like peat, or like some other types of soils which are very organic soils, which tend to be oil wetting, or like different. They're not water wet, but most of our systems tend to be what we call water wet systems. So the only way to get rid of this water is to evaporate that water. Okay, but as I go deeper, I don't get much sunlight. Okay, so there you can heat up the upper portions, but it's very rare, very difficult to heat up the lower portions. So as a result, for most part, our system is water wet. Okay, so I have two fluids in my pore space. What do these two fluid spaces do? Like, what do these two fluids do? Do you think they get along and they are happy? You think air and water, they are friends, or stay there, they're okay? What happens is the air tries to push the water out of that pore, and the water tries to push the air out of that pore. So when you have more than two fluids, each fluid is trying to occupy as much space. What do we know about gases? They occupy the space of the, or any fluid, is that they occupy the space that they have, right? I mean, they spread around and move. And that's what air is trying to do. That's what water is trying to do. So there is pore space. Okay. And I'll also put something here. So this is the pore space. Okay. Now I have some water here. Okay, this is all water. Okay, and there is air. This is all air that's pushing onto it. So this air is trying to push this water, and the water is trying to resist and push it back. But we said it's water wet. Okay, so right on the surfaces, the adhesive forces are water. Water has forces of adhesion that holds it to that rock matrix. Okay, and the air is trying to push it. Okay. What will happen? It's almost like having a little capillary. Okay. This is my pores, and I have air pushing it, and then the water forms a meniscus and is held in tension. Okay. The smaller the pore, the lower the cross-sectional area. So force per area is the stress, goes up. Okay, and this phenomenon is called what? Surface tension. Okay, so if it's between air and water, we call it surface tension. A more generic term is to use what's called as interfacial tension. Okay. So the water here is held. There are two forces acting on the water here. One of it is the gravity, which is trying to pull it down, and the other one is this interfacial tension, which is trying to keep the water where it is. Okay. So water moves very, very slowly in the Vadose zone. Okay, because it has to overcome that capillary pressure to actually move down. Okay, if it can't overcome the capillary pressure, it just stays there. Okay, the more water there is, the less will be that capillary pressure, because most of the pore space is occupied by one fluid, so gravity will take over. Okay? But the less water there is, the more is the capillary pressure, because there is a lot more air that's trying to push, and the grains are saying you can't go anywhere, like there is forces of rotation, so it just stays there. Okay? So that's the Bayes zone. So most of the transport there happens pretty, in one dimensional, or approximately one dimensional. Okay? And as it hits this water table, okay, water in that is moving mostly in the horizontal direction. Okay? Because there is no more capillary action here. There is no more capillarity. Okay? Because my pore is completely filled with water. There is nothing pushing it, like it's just sitting in the walls. So water moves from high head to low head. So there is gravity that's moving this water, but there is all this mass of soil and houses or whatever we have all pushing down on it. So there is a little bit of pressure on that system. Okay? And in addition to that, there is gravity that's moving that water in one direction. Okay? So the water here moves, and as it moves, it takes with it all the contaminants that are dissolved in it. Okay? And we have a house, got a well, we pump water. Whatever is in that water also gets pumped with it for free. So we want water, but we get all the chemicals that are in that water, or pathogens, or microbes, or whatever be it. Okay. So what we are interested when we say groundwater transport is tracking that chemical from its source all the way to where we get exposed. Okay. And that's what. So what we do when we do fate and transport models or groundwater transport models is trying to find mathematical expressions that help us model this system. Okay. Now, where is the complexity? The complexity can come in many folds. Okay. The first complexity is, as this moves, okay, it is not just the flow of water that causes the chemical to move. Okay. There is also other processes, particularly diffusion, dispersion, which can also cause this process, which can also cause movement. Okay. So if I take just water, static water sitting in a glass, and put an ink, a drop of ink in it, okay, it will eventually become blue. That's diffusion, basically. Dispersion is diffusion on steroids. So there is mixing going on. If I mix it, the movement is a little bit more. And because the water is moving through pores, it takes a very tortuous path. And because it's taking a tortuous path, it tends to get mixed. Okay. So, but that mixing is not complete. Okay. So if you're environmental engineers, you know reactors, right? Okay. How many of you are civil environmental people? So you all know what reactors are? Okay. So if I look at an aquifer, is that a batch reactor? Is it a completely mixed stir tank reactor? Is it a plug flow reactor? What could it be? So batch reactor means there's no flow. Okay, we can rule that out because there is flow. Okay, if it was a static system, then that's batch reactor. So it's not a batch reactor. So is it a completely mixed reactor, or is it a plug flow reactor? Correct. So this is what we call a mixed flow reactor or a plug flow with mixing, because it moves like a plug flow. Plug flow means there is no mixing whatsoever. Okay. When would we get plug flow? When the velocity is high or when the velocity is low? When the velocity is relatively high, the water just shoots like a jet, so there is no mixing taking place. Okay. On the other hand, if the velocity is low, now you have diffusion, you have time for diffusion, you have time for mixing, so you can get some mixing going on here. Okay. We don't have a completely mixed reactor because the mixing is not complete. So we have an incompletely mixed plug flow reactor or an incompletely mixed CFSTR, however you want to visualize it, but it's not completely mixed. Okay. But there is some mixing that's going on. Okay. So what rate will this water move? How fast do you think water moves through an aquifer? Approximately. Centimeters per day, per hour, per year. Okay, so centimeters per day to centimeters per year is kind of the typical range. Okay, if you have it in centimeters per year, you won't. It's probably in the clay. You have a lot of clays. If it's in centimeters per day to almost like tens of centimeters per day, you probably have nice sand and gravel. That's where you need to put your well. If it's centimeters per year, don't waste your time and money putting a well. You'll not get water, so it's not usually worried. Okay, so it takes about even just to round it up, it might take a meter a year to move. Let's say like a meter a day. Okay, and if your source and your contaminant, your well, is about 1,000 meters apart, so let's say you had a spill a kilometer away, how long will it take? So you're moving 1 centimeter per day, right? Or even worst case, like let's assume 10 centimeters per day, and you're a kilometer away. Even if let's round it up. Now you have a nice little aquifer, about a meter per day. Okay, 1 meter per day. You're 1,000 meters away. Takes you what 3 years for that mass to get there. Okay, chances are it'll get there sooner because of dispersion. It'll last longer because of dispersion and other factors, but in general, the movement is very slow. Okay, so is that a good thing or a bad thing? Good, bad? How many think it's good? How many think it's bad? Good, right? Well, here's the complexity. Okay, this one leaked. Okay. No one knows, or even person who owns it probably knows it and says, I don't know, it leaked. Okay, you don't know what happened, right? Okay. Thanks. Okay. All right. So what happens? So nobody can see when this spill happened. Okay? And now it's taken like probably 3 to 5 years before you start detecting at your well. Okay? If I had known the spill had happened, it's a good thing. I have 3 years to get out of that place, okay, not use that water. But one of the key problems with groundwater and groundwater pollution is we don't know when that spill happened. Okay? Because it takes so long to move, in some cases it might take like 10, 20 years before you start seeing the contamination at that well. By that time, that industry is long gone. Like by that time, like who knows what happened, right? Like so a lot of times it's very hard to say what caused the contamination. Okay. So one of the differences between groundwater transport and surface water transport, or like contamination, is the timing. Okay. It takes a long time for the contaminant to get there, but it also means that if I don't have a well, I cannot detect. I can go on contaminating this aquifer for years and years and years, not knowing that I'm contaminating the aquifer. Okay. And that creates a lot of problems, because once it's contaminated, then especially in the US, what we do is we say, well, who caused the contamination? Because we want that person to pay for cleaning up that site. Okay. Now, this contamination happened 50 years ago, like, the current owner will say, I never did it, like, then the previous owner did it. The previous owner is like, no, 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 I was not the owner 50 years ago, like, so it goes on and on and on, like, so the lawyers end up making a lot of money. And, as engineers, you tend to be called as expert witnesses to say, what do you think has happened? Like, so I've testified in cases where people are trying to estimate when did this leak actually happen. Okay, so we use a variety of techniques like, fingerprinting, chemical fingerprinting, all kinds of stuff, isotopes, to try to figure out what's a likely time when this contamination happened. But it's generally a bad thing, because when our leaks go undetected, okay, so if we have gas stations, right, we have like, petrol bunks as they're called in this country. There is a tank. Where does the petrol come from? Okay, so you open it and you start, filling your tank. There's a tank underneath, okay, that has petrol in it. Okay, that tank may leak and spill petrol into the Vado zone, and eventually that petrol will make it into groundwater, and it'll start moving. Okay, and 3 years down the road, that well might start smelling funny. It might start smelling like petrol. Like, you pull out the water and you're like, why is it smelling like petrol? That's a possibility. The worst situation would be there is enough petrol in there that it catches fire. Like, so there are instances where water has caught fire just because there's a lot of it. Okay. Now, if you all know petrol, if you have seen petrol, what do we know about petrol? Do you think it mixes with water? Is that a good thing or a bad thing? It's very good, because otherwise people would adulterate it with water, and you would get water instead of petrol, like, so so probably a good thing. Okay, but does petrol dissolve in water? Is it completely immiscible? No. So if I put petrol in water, what do you think? Will some of that petrol get into that water? A little bit, maybe. Okay. Most of it will float on the surface, right? You will see a nice sheen whenever it rains. If you're walking by a petrol bunk, you will see like a nice little sheen. It gives you out like nice rainbow colors, like, so a lot of it is just floating. But it doesn't mean that it doesn't dissolve. Okay, it does dissolve a little bit. So if I look at component, what goes into petrol? Does somebody know chemical formula of petrol? What do you think? You've used petrol, right, all your life, like, you've filled up your gas in, bike or whatever, like, car, your dad's car, whatever, right? You've been dealing with petrol all your life. Did you ever stop and think, what could be the chemical formula for this petrol? What's that? So it's a mixture of alkanes. It's got a mixture of things. Typically, we have C4 to C12 compounds. Okay, it's got aromatics, it's got alkanes, it's got a whole bunch of other things. Okay, the aromatics are really the problematic components of petrol. Okay, so what are the aromatics? What are aromatics? Right, benzene, toluene, ethylbenzene, xylene, like, whatever. They're called aromatics because you can smell them. That's what gives the smell to the petrol. What's benzene? That's a right, C6H6. Okay, so let's focus on C6H6, the benzene, which is about, in a typical petrol, about 2-3% of it is benzene. Okay, so very small amount. Okay, benzene. If you get exposed to benzene, benzene is one of the very few organic compounds that is classified as a carcinogen. Okay? There are many organic compounds which get classified as potential carcinogens or suspected carcinogens, okay? Which means we don't have enough evidence to say that they cause cancer. Okay? Benzene is one of the very few compounds that, especially in the US, is classified as a carcinogen, which means we know it causes cancer. Like, there is no ifs and buts about it. Like, most of the chemicals are what we call suspected carcinogens, because if we don't do experiments where we can subject humans and say, hey, come drink water with benzene every day and I'll see whether you got cancer, right? I mean, how many of you will volunteer for such an experiment? How much money can I give you to do such kind of experiments? Firstly, it'll be illegal on my part, like I'll go to jail. So what do? We find things that don't complain, okay? So we do it on rats, we do it on other critters that are like, and then see what happens, okay? But the problem is they're not as big as us, like they don't have the kind of, resistance mechanisms that we have. So we extrapolate from lab mice to human, okay? Does it scale well? If I shrink you, will you become a mice at some point? No, right? Nobody wants to be that, like, so it doesn't quite scale well. So what happens is when we talk about toxic chemicals or carcinogens or things like that, we are extrapolating, okay? The other way to do it is to go to a site where people have been exposed accidentally, and then see how many of them got cancer, how many of them didn't get cancer. So that's what is called as an epidemiology study. Like, in epidemiology studies, you go and look at people who have been affected and say, hey, why did this person get affected and not this person? Like, or how many person got affected? The problem with epidemiology study is you need a very large sample size, because every human being is different, and like, they are made up of different genetic makeups and stuff. And a lot of times it's hard to find people who are exposed to a certain chemical and nothing else. Like, so there are a host of other things that can cause cancer, benzene being one of them. But benzene is a known carcinogen, okay? So if I take benzene, if I take a beaker, okay, put some water, put some benzene, okay? Benzene is lighter than water, density is about like 0.8, okay? Water has a density of about 1 milligrams per centimeter cube. So benzene floats on water, and I leave this system, okay? So the beaker, initially there was no benzene in this water, okay? I keep the beaker out there for a couple of days, or 5 days, 10 days, whatever, come back, pull out a water sample, and measure for benzene. Will I detect benzene? Will I find some benzene in there? Yes, because some molecules of the benzene decided to move and get into water, okay? There will also be some molecules of water that will get into benzene, but that's not of interest to me. I'm looking at what's in the benzene, okay? How much benzene do you think? If I had 1 liter of water, how much benzene do you think I'll have? Okay? So that's the solubility of benzene, okay? That depends on temperature, that depends on pressure and whatnot, but typically at about 20 degrees Celsius, it will be 1750 milligrams per liter, okay? What do you think the drinking water standard for benzene is? Five micrograms per liter. Okay. So this is how much? 1750 times 1000 micrograms per liter. This is 5 micrograms per liter. Okay. So this is relatively small. How much salt can I add to water? What do you think the solubility of salt is in water? Have you been to ocean, or have you been to a sea? There's about 30,000 milligrams per liter of salt in it. You still don't see it. It's dissolved. Okay? It's only when the water, if you pull that water out and you evaporate it, you will find salt there, but otherwise salt is dissolved. You can actually put more than that. You can put about 100,000, 50, 70,000 milligrams per liter is possible. under ambient temperatures and pressures. So comparatively, this is a very, very, very small number. Okay? But what makes it a contaminant is that 5 micrograms per liter, or the regulatory limit of 5 micrograms per liter. So we can get sick and potentially get cancer if you get exposed to 5 micrograms per liter for a long period of time. Okay? The solubility is still very small. Okay? In terms of mole fraction, if I had 1750 milligrams per liter of water in 1 liter of water, do you know how to calculate the mole fraction? How many moles of benzene is that? Very, very, very tiny amount. Okay? So the reason we worry about contamination is even chemicals that don't solubilize much can be problematic, because even at very low concentrations, they can cause health risks. Okay? So you might not even detect it, or you might not even see it. Obviously, we can detect 5 micrograms per liter. Otherwise, we can't put a standard that based on what we cannot detect. We can actually detect these days, if you have a fancy GCMS or GCMS-MS, you can detect to about 0.05 micrograms per liter fairly easily. Like, so you can detect about 2 orders of magnitude smaller than the standard. But we are dealing with very small, tiny concentrations, dilute solutions, extremely dilute solutions. Okay. The key concept is contamination typically arises in the Veda zone, moves down, and it moves horizontally, roughly horizontally along the direction of groundwater flow, and somewhere you hit a well and you capture it. Okay. So if I had a site like this, how would you go about cleaning it? Okay. What would you do? What is the first thing you would do? The first thing you want to do is, if there is a tank, you want to find where the tank is and get rid of the tank. What's the second thing you want to do? Dilution? This soil is all contaminated, right? So if possible, we want to get rid of that soil, because as long as the soil stays, every time the water leaches, it will create contamination. Okay. What about groundwater? Can we just pump groundwater and clean it? Why not? Why can't we pump groundwater and clean it? I have a well, I can put a pump, move that water out. You can set up a nice little bioreactor or CFSTR or whatever you want to set up, whatever you learned in your environmental engineering class. Why don't you set it up and clean it? What could be problematic? Right. Right. Correct. Right. So when you start doing that, that's precisely what will happen. As you pump water, some of the water in the well is coming from this plume. Some of the water is the fresh water that's outside the plume that also goes in there. Okay. The minute it gets mixed, it's getting mixed. Our problem is we want to take it down to 5 parts per billion, like 5 micrograms per liter. Okay. And even if I had, like, say 50 here, and I dilute it by 10, it will come down to 5, which means I have more water to treat to bring it down to that low levels. And as a matter of fact, that was what we first thought was the way to clean up in the 80s. When groundwater contamination became a big issue in the 1980s in the US and subsequently in the rest of the world, our first thought was we will pump and treat. Okay? So we'll pump the water out and treat it, and then we'll re-inject that water back, and life is good. Okay? What we quickly realized is that it's not possible to do that, because the time it takes to clean that way is just way too long. Okay? It's not easy to just pump all this water out, clean it, and then put it back. Okay? Because every time we are pumping water, we are mixing some clean water, which is getting contaminated because our concentration is so low. So it would take years, decades sometimes, if you want to run this pump and treat system. Okay? And it would be highly cost prohibitive to run it, because you have to keep running that pump day in, day out, for years and for decades. Okay? So the pump and treat was our treatment system of choice in the 80s, even in the 90s. Even now we do a little bit of that, but we have kind of moved away from doing ex situ treatment to more in situ treatment. So we want to go and treat the plume where it is, as opposed to treat it, pull that water out and treat it. Okay? We still do that to some degree. In some places, that's probably the only thing we can do, because we simply cannot go and put a well here or put a well right here, because there's a house in there, or there is highly urbanized areas. So we just can't go and put a well wherever we want to do in situ treatment. So we end up doing ex situ treatment where we have to pump. But we now recognize that it takes a long time for us to do it. Okay? So the upper portion, I labeled it as unconfined aquifer. What's an unconfined aquifer? Correct. So this Vadar zone, as I said, has air in it. Okay? If that air is static, it will be at the same pressure as the atmosphere. Okay? So which means this water table, the surface of the water table, will be at atmospheric pressure. Okay? So the way we define unconfined aquifer is by saying that the water table, which is the boundary, is at atmospheric pressure. Okay? As I go down, what happens to the pressure? It increases. Okay? So, but the surface or the water table is at atmospheric pressure. The reason it's at atmospheric pressure is because there is air in that Vadar zone, and you can actually connect that airway back to the atmosphere. So if that air is static, that means that the pressure is atmospheric. Okay? So that's how we define unconfined aquifer. So we might also have what's called as a confined aquifer. What's a confined aquifer? It's obviously, as the name suggests, there is a confining layer. So there is usually a small layer. Sometimes it can be thick, and made up of very low permeability material. Okay? So we have sands up in the unconfined portion. We'll have sands in the confined portion, but these confining layers are shale or clay or something that's of very low permeability material that kind of separates out my unconfined from the confined aquifer. Okay? So I have contamination here in the Vadar zone. Depending on where that water table is, that contamination can infiltrate and get into my unconfined aquifer for sure, and then move horizontally, or move along that groundwater flow direction. As it moves, it kind of spreads because of mixing and creates a plume. Okay? Can this contamination go into confined aquifer? Is it possible? Okay. So this confining layer, although we call it a confining layer, there is no material that's truly non-porous. Okay. So there will always be some small pathway that will cause some of this contamination to move into confined aquifer. If it's very, very small, it gets diluted, so it's not a problem. But one of the big issues this confining layer does is, if you have some contaminant trapped in this, in this layer. It will sit there for years and years and years, and you really cannot put a well to pull it out. Okay. And it's too deep for us to excavate and pull it out. Okay. And so it gets contaminated, and it stays contaminated for a very long period of time. So there are a class of chemicals called dense non-aqueous phase liquids, or DNAPLs. Okay. Trichloroethylene is a very classic example. These are organic chemicals that are denser than water. Okay. If they are lighter than water, they'll float on the water table. If it's denser than water, it will actually penetrate and go inside. And as it goes inside, some of it might get trapped in this confining layers. Again, we don't need a lot because our concentrations at which we are worried about our health is very, very small. Okay. So it will sit there, slowly bleed into water, slowly bleed into water, and we have spent billions of dollars in the US and many parts of the world trying to get rid of DNAPLs. There's really no technology that's available for us. Like, I mean, a lot of times we don't even know where it is sitting, primarily because the leak happened 50 years ago, or like 100 years ago. We have no idea where it is, and the only thing we can hope for is we can put a well, and we can measure the concentrations, and if it shows too high, we know there is a source somewhere, and we have to go chasing that source. On the other hand, when we don't find it, then we'll say, okay, there's no, but sometimes it might show up during certain periods because the water will just leach out and go to that well. Other times when there is no infiltration or there's no leaching, we may not see the concentration. So we see a lot of rebound in that data, like shows up sometimes, doesn't show up sometimes. So it creates a huge problem in terms of regulating the sites, because we may not see it for 3 or 4 years, and we say, okay, we'll close this site. There is no more contamination, and then suddenly there is a rebound, or there is a spot that comes back up, and then the site gets opened again, and then we have to clean the site back up again. So, but conceptually, contamination can take place in both confined and unconfined aquifers. Majority of our contamination will be in the unconfined aquifers. Typically, the source is not here but here, okay, and there could be multiple sources, and our goal is to somehow take this system and condense it into mathematical equations using conservation of mass and any other expressions that we have to define mass transfer, to define dispersion, diffusion. So we try to take all the physics that we know and put it into our mass balance. And to do that, the key elements are what I talked this morning: the loading terms and the flux terms. So we should be able to calculate flux. We should be able to calculate loadings associated with various processes. Okay. One other thing about aquifers: how much oxygen do you think is here in the Vadose zone? If I take a water sample from that Vadose zone and measure dissolved oxygen, what do you think would be a typical value? Okay. One of the things about being an engineer is having some numbers in your head. Okay. So, what differentiates engineers from other people is we should be able to throw out numbers. Okay. So if someone says, "What do you think is there?" you might not know the exact number, but you should have an idea of what that number could be. Okay. If I take a water sample in a stream, what would be the dissolved oxygen? What pH or dissolved oxygen? 4 to 6. Which stream are you sampling? Okay, so somewhere it's impaired. Okay, 4 to 6 would start killing fish. More than 6. Okay, typically it's about 8, 7.5, 8, 8.5. If it's a cooler day, it might go up to 10, 12, 14. But if you're starting 5s and 4s, you're killing fish. Okay, there's not enough oxygen in there. Okay, still a very small number, right? 8 milligrams per liter. That's typically what you would see in the beta zone. Okay, because it's just like there's atmosphere that has oxygen, and that oxygen is being given to the water. Okay, everybody knows Streeter-Phelps equation. BOD, DO, SAG, same concept. Okay, so what about here in the unconfined aquifer? What do you think would be the dissolved oxygen concentration? Greater than 8, less than 8. Let's say in the Vera zone it's about 8. Okay, would you expect it to be more or less? Less. Okay, so typically in an unconfined aquifer, your numbers are somewhere in the 3-4 range. Okay, of course, we don't have any fish in there because there are too many. The pores are all filled with sand. So, but that's typically where we are. If you go into a deeper confined aquifer, what do you think the number would be? Less or more? Even less. Okay, so typically that would be less than 1. 1, is what you would typically see. So you are under very anoxic conditions. Okay, now I throw some organics into it. What happens? I threw some benzene in there. Okay, there's contamination. Okay, so here it's about 8. Here it's about 3 or 4 in the cleaner portion. Here it's about 1 or 2. So oxygen goes down because there is nothing to give oxygen at that point. Like there's a source of oxygen. What about in this plume? What do you think the oxygen would be? Increase? Organic matter is there. So we have some organic matter, CXHX. Okay, right. That would make it what? A triple bond alkyne, but whatever, CHXY. Will give what? You have to balance, of course, it's an unbalanced equation, but usually if I have oxygen, I have aerobes. Or aerobic bacteria. And what that aerobic bacteria does is it uses that oxygen as an electron acceptor, reduces this, and forms CO2 and H2. Okay? So any oxygen that we have gets consumed by aerobic bacteria. Okay? So we quickly turn this system into an anaerobic system because there's very little oxygen to begin with, and we can use up that oxygen very quickly. Okay? So what happens? What are the other forms of anaerobes? We have a lot of iron in our aquifers, right? Huge problem in Bengal. Typically our aquifers contain iron, so we have iron reducers, like iron reducing bacteria. Basically they take oxidized form of iron, Fe3, convert it into Fe2 as part of the respiration process. We have nitrate reducers, nitrate going to hydrogen sulfide, so, and then we have sulfate reducing bacteria, which takes sulfate, takes it to hydrogen sulfide. Then we have methanogens, which basically take methane, convert it into CO2. So as we go through the plume, the outer edges of the plume tend to be aerobic, and the inner edges of the plume, where there is a lot of concentration, tends to be highly anaerobic, so but there are a lot of biological reactions that take place in the aquifer. Even though we don't have a lot of oxygen, you can still sustain aerobic reactions to some degree, but certainly you will have a lot of anaerobic reactions. Okay? And these anaerobic reactions help or hurt to change your chemical from one form to another. Okay? So if I have trichloroethylene, okay, Does anyone know the formula of trichloroethylene? Single bond, double bond, ethylene. So, okay. So I need two more. So this is my trichloroethylene. Okay. What happens? What can I change this to? So there is a process known as reductive dehalogenation. Okay. So what I do in there is I sequentially pull out a chlorine. Okay. So what happens if I pull out a chlorine? I have to replace it with something, and it's a reduced environment, so I have a lot of hydrogen, so I end up reducing it, putting hydrogen. What is this? Dichloroethylene. What if I pull out another? Monochloro. It's actually called vinyl chloride. Okay. But monochloroethylene is just fine. That's ethene. So basically we go from trichloro to dichloro to vinyl chloride to ethene, like, you know. So that's the reductive dehalogenation or the halogenation process. So the halorespirators are using chloride and using up the chloride to give us hydrogen, like, you know. So it's an anaerobic process. Turns out this TCE is a pretty nasty chemical. Okay. Where do you think we use trichloroethylene? Dry cleaning. Okay. So when you bring out your clothes, they smell good. You know, you have that dry clean smell, which as a kid I used to love going to the dry cleaning shop, like, you know, because I smell TCE. So if we formed, so it's pretty nasty. Actually, we figured out that it's actually a dense Snapple. Like, you know, it's got a density of about like 1.2 milligrams per liter, so grams per centimeter cube. So it's a pretty bad chemical, but this is even worse. Okay, so sometimes if the process stops here, if we form ethene, it's pretty benign, like, you know. But if we don't go here, and if we stop here, we have actually made the problem worse. So biological reactions do take place in situ, okay, and those in situ biological reactions sometimes can cause more problems than they can, you know, than they help. Okay, if we can take this all the way down to here, that's a good thing. Okay, we have converted a more toxic chemical to a benign chemical. But if we stop here for some reason, then we have actually created a more toxic chemical than what we began with. So not all biological reactions are good in our case, but most of the times they do help. Okay? So what can we do to treat that groundwater? We didn't want to pump. Okay, so our first choice was to go and say, let's pump it. And we said, no, we can't do that. Okay. What else can we do? We can do in situ chemical oxidation. Well, first thing we need to do is, if I don't do anything, what will happen to that plume? It'll spread, but it'll also move away. Like, you know, as long as the source is there, it's connected to the source. But the minute that source is gone, this is a free plume. Like, you know, it'll just keep on expanding and moving away. Okay, and if the plume moves away from my property into your property, it's a bad thing. Okay, so nowadays there is a new regulation. I mean, there is a new way in which people are asking for rent. You know, so if a contaminant plume goes from one facility to the next door, they're saying you put your property, which happens to be your chemical, on my property for the last 30 years, so you better pay me rent for doing that. Like, you know, so that is the new regulations that's happening in the U.S. Like, you know, so people are giving up a lot of money because the contaminant plume went there. So first thing we want to do is contain that plume within our property boundaries. The way we contain the plume is usually we put wells and we create a hydraulic head that kind of keeps the plume from moving. Okay, so there has to be some hydraulic control of that plume. We can't just let the plume go free because it will go somewhere else. Of course, if you don't have regulations, that's exactly what you want to do, right? Like, you know, so let it be somebody else's problem, not mine. Like, you know, but you don't want to do that. Okay, so that's one thing we do. Next thing we do is we somehow need to now make that plume, concentrations of that plume decline or decrease. Okay. How do we do it? Ex situ method would be to pump and treat. We don't want to do that. In situ method, somebody said chemical oxidation. Okay, how would you go about doing it in situ? Okay. You can do aeration. The key challenge to doing anything in situ is we have an aquifer, so it is not a free flowing system. Okay. So you have a very tortuous path, you have a very heterogeneous path. So you cannot know where your flow lines are. Okay. So the brute force method would be to trench out something, put a barrier here, right? And then as the water moves, or put a barrier here, so that as this water moves through that barrier, it will clean itself out. Like, that's one way to do it. Okay? A more sophisticated way to do it is to strategically put wells and then inject chemicals so that we make sure that we are cleaning it. Both of them are problematic. The trench is expensive. I mean, you know, if you want to trench, and sometimes it's not possible. If I want to put it right underneath this house, chances are that property owner will never let me destroy that house and put a trench. Like, you know, like, hey, we just want to remove your house so that we can put our trench. They'll be like, let me find a new engineer to work on this project. Like, you know, you're out. Like, you know, so that happens. So sometimes we can't do that. The other times, you know, so but if you put a well, if we don't place the well correctly, we are putting chemicals to the wrong place. Okay, so that doesn't help either. So the key challenges of doing in situ groundwater remediation is not being able to get to the chemical. Okay, if you can get to the chemical, we have all technology in the world to treat our problems. But the key challenge in groundwater is we have never been getting to that chemical is, you know, a risky proposition a lot of times. Like, there is a certain probability associated that we may not ever hit that chemical with the technology we are using. Okay. So this is where nanomaterials or nanotechnologies or nano-based things are becoming very popular because they are very, very small molecules. So they'll go into the smaller creeps and, like, you know, go into smaller pores because there is nothing bigger than their size. So they can go somewhere and be able to clean up things. Of course, the downside of that is we don't know what these nanomaterials are, what their health effects are, and, you know, what happens if I keep ingesting, like, you know, drinking nanomaterials for a long period of time. What is going to do to my health is largely unknown. Okay, so we have some technologies which we think will work, but we're not sure of the risks. We have some technologies that we know for sure will take a long time, and it's not a good thing to do. Okay? And in the middle, we have some technologies which have shown success sometimes, not shown success sometimes. Okay? So that's what adds to a lot of lot of complexity. Okay, but how do we define? How do we say this is clean? Okay. If this well were to be a drinking water well, we have standards for chemicals. Okay, and that, for those of you who were in the morning or yesterday, people were talking about Singapore looking at 300 chemicals, or so we have in the U.S. what's called as the Safe Drinking Water Act, which basically says that if you are going to supply water, if you are going to drink water, or if you are going to supply water from that well to people, you better keep all these chemicals below these levels. There are about 109 chemicals that you have to look at and use that, bring them down to certain levels for those 109 chemicals. I'm sure there are similar regulations in India related to those chemicals, and you have to make sure that that happens. What if that well is not a drinking water well? What if you're not using it for drinking water purposes? Do we still clean it to drinking water standards, or should we clean it to drinking water standards? How many of you think that we should clean it to drinking water standards? One person, okay? We have one brave person. Why do you think it should be clean to drinking water? What's that? So it's possibility that, that contamination, if you let it move, can affect the drinking water aquifer, portion of the aquifer. Okay? The other way to think about it is, today it may not be drinking water, but down the road it might become a drinking water supply. Somebody might put a well there or put a house there, so it's possible. So historically, what we have done is try to clean our aquifers to drinking water standards. Okay, and those standards are pretty stringent. Okay, now who can make an argument that we don't have to clean it to drinking water standards? Who can argue with me that we shouldn't be cleaning this to drinking water standards? Okay. Now think that you work for a chemical company that has caused this spill. Okay? And your job is to go and tell the regulatory agency or convince them that you don't need to clean it to drinking water standards. Okay. What argument would you make? Okay, if there are no residential areas, I'm going to say, well, it's not there today, but it will be there tomorrow. So, you are just telling me that you should clean it to drinking water standards, so, right? What other argument can you make? Okay, till that point, everybody is taking a risk. Yeah, then I don't want it to happen. My job is to protect that people from getting sick and getting contaminated. Okay. The question is, where is that water being? Who is drinking that water? Okay. If I were to drink that water, where am I drinking that water? I'm going to drink it somewhere in that house, right? I'm not going to drink water here. Okay. So you can argue and say, I don't need to bring the concentration here down to drinking water standards. What I can do is, I should make sure that this person is getting water that's of drinking water standard. Okay. How do you do it? Well, one way would be, I'm going to leave this aquifer contaminated, but I'm going to give this person lifetime supply of bottled water, so they don't have a problem. Okay, that could be one argument. The other argument could be, I'm going to put a treatment right here. So if I'm a municipal water supply, I'm going to say, I'm going to put a treatment system right there and treat that water. So why do I want to make this drinking water and then treat it again to make it drinking water? Like, that just makes no sense. Okay. So that has been another argument, is to say, when do we call the water is clean? Okay. So there's a lot of legal complications to groundwater transport. So we start using groundwater transport models to make these calculations, to make our case on whether it should be drinking water standards or should not be drinking water standards. If I say that it takes 100 years to bring it down to drinking water standards, as a regulatory agency, would you say, yeah, go for it, it's a good thing, right? Or not? Okay. Some cases, if I were to put a certain treatment technology, it'll take me about 100 years to clean that water to drinking water standards. Okay. Well, what do we know about cleanups? They usually have an exponential curve, which means I can bring it to 90% of the drinking water standards within 10 years, but that last 10% will take me another 90 years to get there, because of the way as my concentrations become low and low and low, the treatment efficiency becomes low and low and low, so it's harder to remove. It's easier to remove the first molecule of the pollutant than it is to remove the second molecule of the pollutant, and it's even more tougher to remove the third molecule of the pollutant, so on and so forth. So that's just the way our treatment works, because all our treatment technologies are driven by some concentration gradient. If the gradient is low, our treatment flattens out, right? So that's another argument that goes on, is to say, when do we call this clean and when do we not call it clean? Okay. Our first understanding, when we first started getting into this business, our approach was always bring it down to drinking water standards, regardless of whether the aquifer is drinking water standards or not. Okay. What we have realized since is it takes a very long period of time to bring it down to drinking water standards. And it may be that the aquifer was never at drinking water standards to begin with. So why am I cleaning up the aquifer to levels that never existed? Okay. So we have kind of moved away from that model. And then secondly, we might say we might not do all of the treatment at once in the aquifer. When the water comes out, we understand that it has to be treated again, so we'll make use of that. So we've kind of moved away from going towards this first standard of saying, yes, let's bring everything down to drinking water standards. We are kind of moving away to more risk-based approach of saying, what is the risk, or who is at risk, or when we don't treat this to drinking water standard. Okay, how do we calculate those risks? Again, we are predicting something, and we have to forecast in the future and say, this is what will happen if I stop treatment today. And for that, we need some model to tell us this is what the concentrations will look like at this well if I were to not pump it, or if I were not to treat it. Okay, so that's one. So coming back to subsurface systems. So our subsurface system has two things, solids and the pore spaces in between. Okay. So there are a few other properties that you probably have seen, but you should know and should be very clear. So first thing is aquifers. Okay, we've talked about aquifers, right? Confined aquifers, unconfined aquifers. What's an aquifer? What's an aquifer? Okay, so it's a subsurface formation that has water in it. Okay, but not all subsurface formations that have water are called aquifers. To classify it as an aquifer, it should be able to provide water on a sustainable or on a consistent basis and sufficient for human needs. Okay, so when we define aquifer, we have a very anthropogenic focus of that aquifer. So it's not all subsurface formations are categorized as aquifers. If it has to be an aquifer, it has to provide water for certain use, and it should be able to do that consistently. Okay, so if I don't have that, then it's not an aquifer. Okay. So the other names are water-bearing formations or groundwater reservoirs. You will see other things being used. Aquifers, as I said, are separated by confining beds. Okay, and common confining beds are aquicludes, So what's an aquiclude? So clay is a good example of an aquiclude. Okay, it's got water in it, but it won't yield that water. Like, clays usually have a lot of water, but you can't pull that water out. Okay, so that's an aquiclude. Aquafuge. So this is like a granite. It neither has water nor will it transmit water, which is why it makes great flooring material, right? Like, it never, there's no water seeping into your foundations from this. Like, you can clean it off very easily. Okay. What about aquatards? So aquatards are relatively impermeable materials that may transmit water, but they don't have a lot of water. So they may not have a lot of water, but they will transmit water. So typically you have clays mixed with sands, or like, sands and silts and clays mixed together form aquatards. Okay. If you are looking for water supply, you will never put a well in an aquatard, okay, because it doesn't give you a lot of water. Okay. But aquatards are extremely important from a transport perspective, because if a contaminant gets into an aquatard, it will sit there, and then the water that passes through it will get contaminated and go into the aquifer, and it will get contaminated. Okay, so the way to remember aquatard is, it retards the movement of water. Like, it moves water very slowly, but it can be a huge problem when it comes to groundwater transport. Like, so if you have contaminated sites, the first thing you want to do in your geologic characterization is to look for those aquatards, because those aquatards are going to be a long-term source. You may remove that underground storage tank, but if that stuff has gone into that aquatard will act as a source for many years. Okay. Vadose zone, we talked about vadose zone. So this is between the top and the bottom. Okay, so the top of the land surface all the way till your water table is your vadose zone. What vadose zone has is 3 phases: solids, liquids. Of the liquid phases, it has got air, water, and air. Okay, so the water is held under tension in the vadose zone. So that's the characteristic of a vadose zone. And of course, the aquifers, the water is fully saturated. Particle size distribution. How many of you remember what particle size distribution is? Do you all know a picture like this? You must have seen in your geotech or in your soil mechanics class. So the way we engineers typically say is, okay, if it's 2 centimeters or more in grain size diameter, it's gravel. Okay, from 2 to about 0.05 are your sands. Anything less than 0.05 is your clay and silt fractions. Okay, in aquifers, how do we get this? What can we do in the lab? So can we get all of this information from sieve analysis? No, only till about here we can get using sieve analysis. This part is what's on your pan. You have to do a hydrometer analysis and then get that part done. In most aquifer characterization studies, if we only do the sieve analysis, we know that it's 2% or 3% sand or silt or clay. We are not really interested in characterizing what the grain size is, but we want to know on a relative basis how much sand and how much gravel do we have. So if you are looking for water in groundwater, you obviously don't want a lot of silt, right? You don't want a lot of clays and silt, because they're not going to transmit water. They may store water, but they'll not transmit it. What about gravels? Do you want a lot of gravels? So you have 2 aquifers, okay? One that's very gravelly, one that has a lot of sand. Okay? Site A, site B. Which site are you going to put your well? How many of you are putting it in gravel? How many of you are putting it in sand? More water will be there in gravel. So how many of you want to put the well in gravel? Nobody. Only one person is getting a lot of water. Okay. How many are in sand? Rest of you don't want to put a well, is what I'm assuming. Like, well, you have no choice. You have to put a well. Like, so why not he said in gravel there's more water, so he prefers gravel, right? Why don't you prefer gravel? Well, I've got a nice little borehole. I mean, I'm not going to manually put a well. I'm going to drill it through. If I have to break that rock, I will. I have equipment to break it. So gravel has a lot of big pores, right? So there'll be a lot of water. Okay. So why not put it in gravel? Connectivity is beautiful. Okay. It's got nice big pores. One pore connected to another pore. Okay. So it's very easy to pull water out of a gravel because the pores are very big. Okay. Which means your water will get drained, your aquifer will get drained very quickly. You can pull a lot of water, but you won't pull a lot of water for a long period of time. So our consideration always is we want to pull enough water, but we should be able to pull that water for next 30 years, 40 years. If you're a municipal water, if you're putting a well for a municipal water treatment, you at least want that well to serve you for another at least 10 years or 15 years because you're spending a lot of money putting that well and you don't want it. So the sands are really the best places to put. Sands with a little bit of gravel are really the best aquifers because it's not just how much water they have, it's how they transmit that water. Okay. If they transmit that water too quickly, you will end up draining that water. If you have clays, they have a lot of water, but they don't transmit it. So, you will keep on pumping, but the water doesn't come out. You know there is water, but it's not going to. So the sands give you a nice little happy medium in between, where you can pump appreciable amounts of water, but at the same time you're not dewatering that pores very quickly. If you dewater that pores very quickly, it's done. That well can be tossed out. You'll have to put a new well. So extreme gravels are problematic. Extreme clays and silts are problematic. So we typically try to put our wells in sandy formations. We try to be more on this side than on this side. So we would like to have some gravels to give us that transmissivity, but a strictly gravel well will not last very long. Okay. Soil classification. So engineers do what's called as an AASHTO classification. What do we use for our classification purposes? So there are a couple of ways in which we can classify soils. Okay, as engineers, how many of you are civil? How many of you have done a soil mechanics lab? Okay, what are one of the after grain size distribution? You do two other things. What are they? Soil mechanics is one of the fun labs to do, right? Generally speaking, you can get dirty and. So how many of you know what a liquid limit is? What's a liquid limit? How do you measure liquid limit? So you have a little cup called a Casagrande apparatus. You fill it up with soil, and then you rotate it for 25 times. You hit it, and then once it joins, you know how much it is. That's your liquid limit. I mean, every other engineers will laugh at us for doing liquid limits, but it has helped us a lot in trying to do constructions if you do. And what's a plastic limit? Yeah, you take the soil and then you roll it, see when it breaks, and then you calculate the length. That's your plastic limit. So typically in an AASHTO classification, which is the American Association for Highway and Transportation, their classification, we make use of our grain size distribution as well as liquid limit and plastic limit to classify our soil. The reason for that is, as civils, their interest most of the times are in knowing the strength of that soil. Okay, they're not interested in the water. Water for them is usually a problem. What they're interested in is how much load can that grains carry, because that's what helps the foundation stay where it is. Okay. Now, if you're on the water side, you're more interested in the water. You don't really care about the liquid limit or the plastic limit or the strength of that soil. What you're really interested in is how big are the pores and how easily can water flow from the pores. So the USDA classification is what we typically use. This is the US Department of Agriculture, and the way they do soil classification is by plotting it on what's called as a ternary diagram. Okay. So on one side you have sand, one side you have silt, one side you have clay. Okay. And depending on how much sand, silt, and clay you have, if you have a lot of clay, of course it's classified as clay. If you have a lot of silt, it's classified as silt, and this black line here, and then it's also classified as sand wherever there is a lot of sand, sandy clay, sandy loam, and here's your sand. Okay. How do you read this chart? Okay. Even though it has three axes, your sand plus silt plus clay should come out to be 100%. Okay. So really it's a two-dimensional chart. Okay. The way to read this chart is you follow the direction in which the number is written. Okay. So if I have 70% silt, I go to the 70% line, and that's my silt line. Okay. And if I have, let's say, 15% of sand, then I go to the 15% line. Wherever they intersect, the remaining will be 100 minus those two, so it will fall there. Okay. So depending on which box they fall, we can classify them as clay, sand, silt, so on and so forth. Okay. But one thing is, this was developed by agricultural people, so you will not see gravels here. Okay. You will not see boulders, rocks. Everything is sand, silt, and clay. The reason for that is, if it's a big rock, it's useless for agriculture. Like, you can't put a plant on it. So they get rid of that and only look at sand, silt, and clay fractions. Okay. So your sand, silt, and clay should add up to 100%, which may not always be the case. You may have boulders, you may have big rocks, you may have gravels, but all those get removed, and then you take your sand, silt, and clay fraction and make that 100%. So phase properties, bulk and particle density, which one is a bigger number? Why? So what's bulk density, what's particle density? So you have soil, right? So you have solid or water, air. Okay. Let this be total volume. Okay. So I have mass of solids, mass of water, mass of air. Okay. What's the mass of air? Zero. Okay. Okay. So how do I define my bulk density and particle density? Okay. Similarly, I can have volume of solid, volume of water, volume of air. Now these volumes are not zeros. Okay. Air will have a finite volume. It might not have a lot of mass, but it still has a volume. So how do I define my bulk density? Right. So by convention, we neglect MW, even though MW might be adding some mass. Okay. By convention, we say we're not going to account for it. And what about rho s? So what is the relationship between rho b and rho s? So you know how to derive it? from basically this, and we also know that is your porosity. So volume of water plus volume of air, which is the volume of voids, is my porosity. Okay, now we have something called voids ratio. What's voids ratio? So which one is bigger number? Porosity or voids ratio? Always? Is there any time when your porosity is they may be equal? When will they be equal? Fully saturated with what? Correct. If there is no solids, then you have a hollow pipe. Your voids ratio and porosity are one and the same. But that's the only time. But it never happens for us in groundwater because we always have solids. Otherwise, we don't have groundwater. We have open channel. So bulk and particle density. Why do we need this? Where do you think we can use bulk and particle density? Capacity of the aquifer, possible, but one big place where we use bulk and particle densities is making sure our concentrations in solids are written correctly. Okay? So, what is the So I told you that the concentration of so if I take soil, right, the way I take a soil sample usually is using some sort of an auger. Okay? So this is a hand auger. So if I have a very shallow soil, the way I would take this sample is to use what's called as a hand auger. I would push this, pull it out, and I'll get soil. Okay? Would this sample be disturbed or undisturbed? Undisturbed? Somewhat disturbed. There is no such thing as an undisturbed sample. Okay? Never happens. Okay? We may call it undisturbed because it makes us feel good, but reality is we don't have it done. It's always disturbed. Okay? If I remove it from the soil, from where it is, I've disturbed it, like somehow or the other. Okay? So, so hand auger, would you just push it down or would you twist it? The more you twist, the more disturbed the soil becomes. Okay, the more you push, the less disturbed it is. But there are times when we can't push it, so we'll have to twist it a little bit. But we get our soil sample. The other thing we do is sometimes we shave off because right where that auger is, that's where our disturbance is. Okay, so sometimes if we have clays, we take the sample and essentially shave off the sides, so that the inner core is relatively undisturbed. So we try to get that portion. Okay. So if I want to look at a contaminated soil, right, and I want to know what is the concentration, so that I know that my soil has solid water and air, right? And let's say I want to know what is the concentration in the water. Okay. So how do I get that? How do I measure it? Okay. So when I take the sample, I can only take the sample of the entire soil. Okay. Because in the Vero zone, it's very hard for me to get the water sample by itself. It's possible, but it's very difficult because there's not much water. Okay? So I have very little water. So because of that, chances are I don't usually measure what's the concentration. I can't separate out that water. Okay? What I get is the total concentration. You get the total soil. Okay? So I can take the soil, I can pull an auger, pull the soil out, and extract everything there is in that soil. Okay? Usually I'll put this into a solvent and then extract out everything. But what I'm doing when I do that is I'm extracting what's in the solid phase, I'm extracting what's in the vapor phase, I'm extracting what's in the liquid phase. Okay? So somehow I have to, from there, back out what's in the air phase, what's in the water phase, what's in the solid phase. And knowing how much mass transfer is taking place between these, I'm able to calculate that. Okay? So we'll look at that calculation, a few classes down, but it's one of those times when we need to use bulk density and particle density, to figure out. Another concept, probably the last one, that how many of you have measured porosity in the lab? A falling head test and a constant head test. Again, you must have done this in your geotech labs. If you have clays, would you do a constant head test or a falling head test? Falling head? Why? Correct. So if you want to do a constant head test, you need to have a very high head to literally push that water through that clay, and that's usually not. So the falling head test helps us when there is clay. When you have sands which drain very quickly, or gravels, doing a falling head test is very difficult because the water drains very quickly. So you end up doing a constant head test. But both are ways in which we calculate porosity, or we can calculate hydraulic conductivity. The last concept that we'll talk about is the storage coefficient, or the storage storativity. This again is a very important concept when it comes to measuring aquifer yields. And so if I have an aquifer, let's say my water table was here, okay, and I pull out a known volume of water. Okay. What happens when I pull that water out? What will happen to the water table? It will go down. Let's say it went down by delta H. Okay. And I pull this water over a cross-sectional area A. So my storage coefficient delta H. Okay. So this looks, since I know this is all saturated, right? This very much looks like porosity, but it's not equal to porosity. Okay? Because this is the volume of water that I'm pulling out per cross-sectional area. So it's some sort of a flux, but there's no time involved. But instead of the time, I have the change in head. Okay? So this is called the storage coefficient. In unconfined aquifers, I'm pulling water against gravity. Gravity is the only mechanism that's causing the water. The gravity is pulling the water down. I'm trying to pull the water out, which means I'm pulling the water against gravity. Okay? So then, and only then, it is called okay? Another word for specific yield is drainable porosity. Okay? So this is the amount of water that you can drain under the influence of gravity. Okay? So do you think specific yield will be bigger or smaller than porosity? always, okay? Only when there is no pores that it becomes equal to porosity, but drainable porosity is always smaller than porosity. Porosity tells us how much water is in the aquifer. Drainable porosity tells us how much of that water can we actually extract. Okay. So you just told me that drainable porosity is always less than your porosity, right? Which means, what do we know about the aquifer? Correct. We cannot pull out all the water that's in the aquifer. It's not possible. Because as you pull the water out, you'll displace it with air. And if you displace it with air, at some point there is enough air that the capillary pressure becomes so high that water will stop moving. Okay. So in most aquifers, 30 feet or 10 meters, if you pull the water down to 10 meters, that aquifer is useless. You can't pull any more water. Okay. So that's how we define the usable life of an aquifer. So what I covered today was all part of the chapter 1 of your notes that I gave you. So go over them, and then if you have any questions, we'll pick it up from there and talk some more tomorrow.
Sir, how will you define specific storage?
Oh, we'll get to that, okay, because that has got to do with the compressibility of the aquifer. In confined aquifers, the mechanism by which the water releases is slightly different, so I'll talk about it, and that's where this concept of specific storage comes into play. Okay? Because you have to look at the elastic properties of the aquifer. So we'll get to that. Other questions?
So why shallow water table are so contaminated? I mean, if you get the pump out and if there is no shallow water table, I mean, water table is near to the surface.
Right. You're closer to the sources. You're closer to the sources of pollution.